Okay, so today we're going to talk about the binomial distribution. And remember, the conditions for something being binomial, it must have two outcomes. We classify them as success, fail, although success and fail do not necessarily mean success or failure. It's simply we're calling whatever we're looking for the probability of success. Whether or not that is success is going to jail. Lots of observations of success fail. Living or dying would be a success fail. Clearly, interpreting this would be probability living would be successful, but often we'll be looking at the probability of dying from something, and that would be classified as our success for binomial. So don't interpret success fail in any way related to them. The probability of success must be fixed for it to be binomial. Every observation must have equal probability. All observations are independent. They must not be changed by any other observation. And a fixed number of trials or observations is required. Functionally, this is answering the question, is the probability of X successes and N observations. That is binomial. So we're going to talk about what is a binomial distribution. So we're going to talk about Corinne's free throws. Corinne is a basketball player who makes 75% of her free throws. In a key game, she shot 12 free throws and made only 7. We are interested in, did Corinne just let the nerves get to her? Or was this just within the general realm of binomial? So first thing we're going to do is check, is it binomial? Or I should say, is it in the general realm of chance variation? So we're going to check, is it binomial? Does it have two outcomes? Yes, make or miss. Probability of success is fixed. She's a 75% free throw shooter, so that's fixed. Are free throws independent? They should be. Is it a fixed number of trials? Yes, there are 12. So this is a binomial setting. And I am going to do, so I'm interested in a binomial, and I'm interested in what's the probability of making X. Well, X is going to be the number of free throws she makes. And one of the key things is here is she could make 0. She could make 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or she could make all 12 of them. To do this calculation, I'm going to use a calculator. Okay, so I'm going to switch over to the calculator screen here. And I'm going to start a new document. I'm going to add a calculator. And to do this, I'm going to do menu probability distributions binomial. And we're going to do what we call a binomial PDF. So I did probability distributions binomial PDF. And I'm going to select that. And it's going to ask me for n number of trials, 12, probability of success, P, she's a 75% free throw shooter. I'm interested in 7. And it tells me, so n was 12.75 and my x value was 7. And it shows me this. If you're doing this on the AP test, you'd want to write that line down. And it gives me this value. There's a 10% chance, roughly 10.3% chance, that she'll make 7 free throws. That's not terrible. But if I'm interested in knowing what is the likelihood that she'll make only 7 free throws, I am really looking for 7 or less. So as I'm doing this, I've got this one, but I need to add up all of those ones. Now, one way to do this is to not actually enter that value 7 when I do this on the calculator. So I'm going to do binomial PDF again. So here it is, probability distributions, binomial PDF. And I'm going to leave the optional one blank. And now it spits out this long list. This is 0, this is 1, this is 2. This is a little hard to interpret. So I'm going to store this in something I'm going to call A. Stow is, again, second var, it's above 9. And I used a double letter because I'm using AA because it's easy. Use a double letter. I hit enter. And I get that. Okay, I'm going to clear a few of these out. So I've got some room for some new ones. I'm now going to add a list in spreadsheets. And I'm going to set column A, where is my count? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The reason I have done that, so I numbered this column, is because I do not want to associate the first value with 1. It needs to be associated with 0. So in column B, I'm just going to enter AA like that. And as soon as I hit enter, it fills it in for me with all my values. Now, this is a little easier way to fill in your table. With the calculator, you can scroll down and actually see them all. And we can see the same value we had for 7. Now to get 7 or less, I can add them all up. A little bit of a pain in the butt. There's a lot of them to add up. And they're kind of small numbers, so you have to actually keep the decimals. There is an easier way to do this, however. We'll go back to our calculator screen. And we're going to do probability distributions. This time, instead of binomial PDF, we're going to do binomial CDF. So PDF means probability distribution. So that's going to give us all the individual probabilities. CDF means cumulative distribution function. So here I'm filling it in. I've got 12.75. My upper bound is going to be, and lower bound is 0 to 7. So I'm looking at 0 to 7. There, now it's all filled in. And this is just going to give me a value where it added them all up for me. So my probability that she makes 7 or less is almost 16%. So was she nervous? Maybe. Maybe nerves affected her and she shot worse. But it's 16% tells me it's reasonably within the realm of chance variation that this was a random day where she did not shoot as well on her free throws. Okay, so doing this, I am forced to check I'm forced to at least think that there's within the realm of possibility that this is simply a example of chance variation. Okay, we're going to talk through a couple examples now. So that's kind of the idea of what binomial probability is about. Okay, that's what we would use it for. That's how we're going to work with it. I'm going to talk through, first thing I want to talk through though, is we're going to go through a few more examples and checking if it is binomial. Now that you've kind of got an idea what binomial is and why I would use it, we're going to check if it is. So we can abbreviate binomial distribution first off with B, number of trials, probability of success. So the one I just did would be B 12.75. I'm going to go through this example and we're going to see, is this binomial? Blood type is inherited. If both parents carry genes for O and A blood types, each child has a 0.25% probability 0.25 of getting 2 O genes and so having type O blood. Different children inherit independently of each other. The number of O blood types among 5 children of their parents each count X of successes in 5 independent observations with probability 0.25 of success on each observation. This is binomial because there are 5 observations, fixed number. Success is type O, not O is fail. Doesn't matter for what that really means, if that's successful or not, but that is what we are considering success for this. Each observation is independent and each one has a probability 0.25 of being binomial. So this example has a binomial distribution B5.25. Next one, dealing cards. Deal 10 cards from a shuffled deck and count the number X of red cards. There are 10 observations. Each card gives either red or black. So it's either red or black, counting number of red cards. This is a success fail. However, the probability is not the same for each card. After I've drawn one card, I either have a 25 out of 51 or a 26 out of 51 chance of getting a red card. I do not have a 1 out of 2 chance like I do for the first card. So because the probability is not the same for each one, it is not binomial. Inspecting switches. An engineer chooses an SRS of 10 switches from a shipment of 10,000 switches. Suppose that unknown to the engineer, 10% of the switches in the shipment are bad. The engineer counts the number X of bad switches in the sample. So he counts X bad switches. This is not independent because after he picks one switch, or this is not, the probability of success is not quite fixed because after he picks one switch, he either has 1,000 bad switches out of 999, or he has 999 bad switches out of 9,999. Not quite the same probability for each one. However, those are very, very close probabilities, so binomial could approximate this pretty well. It's not a perfect binomial distribution, but it is approximate. Okay, so that's thinking about how we select if it's binomial. We will approximate our bad switches from binomial with a value. If you look at page 442, they give a graph of the binomial PDF for 0, 1, 2, 3, 4, 5, 6, up to 10 switches, all 10. Now, it makes sense that the probability of getting 0 or 1 would be pretty high, maybe even 2 when 10% are bad. 3 is not real likely, 4 gets really unlikely, 5 is, there's only 10% of the switches and you're choosing 10, it's highly unlikely you'll get 5 bad ones. Although it is theoretically possible to get 10. That probability is more than 0, but it's not much more than 0. Okay? So we could approximate my binomial distribution for the switches. It's approximately, we'll use this symbol for approximately, 10.1. And again, I would use the calculator like I did for Corinne's free throws to get my distribution. And then the histogram I'll probably end up making by hand, but it's very easy to see that histogram on page 442. Okay, I'm going to show you the formula for binomial distribution here. This is for a binomial PDF. You'll be very thankful that you're using your calculator. So this is binomial for, again, Bn. K is the particular value I'm choosing. So maybe it's 7 out of the 12 free throws. N would be 12. K is 7. And that's the formula. N factorial, so 12 factorial over 7 factorial times 5 factorial, 12 minus 7, times P is 0.75 to the 7th. 1 minus P is 0.25 to the 5th. Gee, isn't that a nice calculation? I really like using the calculator. It makes life much, much easier. So somewhere along the line, we've referred to mean as expected value. So the expected value for binomial distribution, well, if Corinne's a 75% free throw shooter, we'd expect her to make 9 out of 12. Or it's simply N times P, number of trials times probability of success. The standard deviation is a little bit more complicated formula. The square root of NP 1 minus P. Okay, so with Corinne's free throws, we said mu was 12, or mu was 9. 12 times 0.75, or 9. Sigma is square root of 12 times 0.75 times 0.25. Which equals 1.5. If n is large, we can approximate binomial to normal. There's probably not a ton of point in doing this since you can use a calculator, but it's a good exercise to get us back into using normal distributions, because we're going to be doing that a lot later. So if n is large, binomial becomes approximately normal. It never becomes exactly, but it can give us a pretty good quick way of doing it if you didn't have a calculator to do it. So our attitudes towards shopping changing. This is page 452. Sample surveys show that fewer people enjoy shopping than in the past. A recent survey asked a nationwide random sample of 2,500 adults if they agree or disagree. I like buying new clothes, but shopping is frustrating and time-consuming. The population that the poll wants to draw conclusions about is all US residents that are aged 18 and over. Suppose that in fact 60% of all adult residents would say agree if asked the same question. What is the probability that 1,520 or more in my sample agree? So at 60%, I can start with the mean. This is binomial. You either agree or disagree. Your probability is supposedly fixed at 60%, the national probability. And every person's attitude is probably independent in my sample. And as a fixed number of observations, 2,500 is my sample. So mu here is going to be NP, 2,500 times 0.6, that's 1,500. So I have a mean of 1,500. I'm looking for 1,520 or greater. 15, that's 20. So I need the standard deviation. That's square root of 2,500 times 0.6, that's P, times 1 minus P, 1 minus 0.6 is 0.4. And I get 24.49. So I'm approximating this binomial distribution. Now, B 2,500 0.6 with a normal distribution, and mean 1,500 is first thing in normal. Standard deviation is second. So in order to do this, I'm doing a z-score. 1,520 is my x value. And I get z equal to 0.8166. So I'm going to look up 0.82 in my table. And I get 0.7910. That is on the left side. So I do 1 minus, and I get this probability of 0.2090. If I use my calculator to do a binomial CDF, from n2500 p 0.6. Here I can do the lower bound as 1520 to the upper bound 2500, and I get 0.213. So 20.9 versus 21.3. That's a decent approximation. Now, it's always better, since you can, to really do the actual binomial, but it gives me a relatively decent approximation. Oh, I looked up the wrong one. That's 2061 versus 213. So it's off by a little bit, even with a large number, but it's not terrible. Okay.